Hey everyone. The next lesson is to do with results that you get from working with exponents. So they call them exponent rules, but it's really just basically the logic of results of what makes sense when you're working with the numbers. So if you're working with the numbers and you calculated the number of coins left over in an activity, you get the right value, right? If you're doing the right stuff. So I'm just going to start out with a quick review of what we've looked at. Exponential growth has a slow growth section and then a fast growth section, so increasing. And the graph could have been like this. It could have started out slow or it could have started out fast, right? So that's just key features of exponential growth, and then very similar for exponential decay or decrease. A fast decrease and then a slow decrease. Tail end. Both equations have the same format where you have the initial value. I'll just label that as well, right there. Right, the initial value, and then the number inside is your growth factor or your decay factor, or based on however you're given information. Key feature to notice of that is if it's greater than 1, it's exponential growth. And if it's between 0 and 1, like 0.5 for that coin activity, 50% chance of all the coins or half the coins getting removed, right? So 0.5 decay factor was the number from that. All right, so here we go for the new stuff when you're working with exponential things. We're going to look at what's referred to as exponent rules. They're just results, multiplying powers. The first one's called the product rule. So to help justify that these are true, the results are logical, what they should be, I'm going to look at the logic based on the numbers. And so if we had 2 to the power of 3, I think we could all agree that this is 2 times 2 times 2, and that's what that means. And then the 2 to the power of 4 means a 2 times a 2 times a 2, 4 of them. So of course those two things are multiplied together, right? So there's a multiplication between those two things, so that's there. In the end here, you can see there's 1, 2, 3, 4, 5, 6, 7 of them, right? So 2 to the power of 7. So what we can do is we can use that logic result to say, okay, well, where do we think that's coming from based on the numbers we started with? And you can easily tell that they were added, right? So the exponents were added. So then as a product rule, it looks like this, where you have exponents of n and m. So you have the n and the m added in the exponent. Okay, so let me just point out you're not doing this, right? So I would say, like, don't do this. This was just to justify the rule that it makes sense, right? So here we're not going to write out 5 3s and 10 3s. We're just going to say, okay, well, based on the rule, we know that we would add the exponents, and so we get 3 to the power of 15. Same thing here. We're certainly not going to want to write out 11 and 32 7s. So we just go 7 to the 11 plus the 32, and we get 7 to the 43. Okay? And it's not about evaluating here. We're just writing as a single power, or what's often referred to as just simplify. Okay, so this is a single power or a simplified version of what we started with. Okay, so that's the power product rule, sorry. The next one we have is the quotient rule. So we'll do the same kind of thing. We'll look at the logic of the numbers here. So a 3 times 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 a 3, 7 of them, and a 3 times a 3. Okay, so if we're looking at that, 3 divided by 3 is a 1, 3 divided by 3 is a 1. So if I put an in-between step here of like 1 times 1, right, for where those were, you'd have the other 3s still. Right, 5 of them, and so that would obviously be written as 3 to the power of 5, because 1 times 1 times 3 times 3 times 3. Same thing as just the 3 times 3 times the 3 business. 5 of them, of course. So same idea. We look at the 7 and the 2 and say, well, what must have happened to make that? And you can tell that it must have been subtract. So that justifies completely the logic of that rule, where we have the top exponent take away or subtract the bottom exponent. So as an example here, we could say, well, the in-between result would be 4 to the 9 take away the 3, so it would be 4 to the power of 6. And notice this could have been written as 4 to the 9 over 4 to the 3, or 4 to the 9 divided by 4 to the 3. They mean the same thing, right? So this one, very similar. We're certainly not going to want to write out all of those. And so this is the logic step. And so it really just becomes 12 to the power of 1 there. Missing 12 to the power of 3, I think it is, right? So this, if you were to evaluate, right, would just be 12 to the power of 3. So we just say, okay, 12 to the power of 3 gives us 1,728. Now, it doesn't work on this calculator, unfortunately, but on a handheld calculator in the classroom, you would find that you can't do this. I check my phone too, see if the phone would do it. I suspect it might. So with the phone flipped sideways, can we do 12 to the power of 3, 4, 7, 1? And it in your iPhone or other calculating devices probably will say this. So my phone says error. The scientific calculator in the Windows operating system is a bit crazy. It can do that one. It still does it. So it's like to the power of 3, 4, 7, 1. And it spits out this gigantic number that would be 6, 888, and so on. And there'd be literally 3,745 numbers. That's how big of a number it would be. If there is a limit, though, of course, in calculation power of things. So if you did like 999 to the power of, 99999, eventually the calculator is going to say, okay, seriously, I can't do that. It's ridiculous. I can't do that many calculations. Okay, there's limits to the programming power. So the idea I'm getting across here is that you can't evaluate this often with most devices. Right? We couldn't just evaluate the individual numbers and then divide them. Calculators and programs just wouldn't be able to do it. But the understanding allows us to be able to do it. So that's just the quotient again. So let's go now to power of power. So power of a power would mean power of 3 means those 3 of those things, right? So we have a 3 to the 2, a 3 to the 2, a 3 to the 2. So that would be a 3 times a 3 times another 3 times a 3 times another 3 times a 3. So overall, you can see there's 6 of them. So that'd be 3 to the power of 6. So same idea. What is happening there? You can tell that it was multiplying. Right? So that is shown by this. So a to the n to the power of m would be a to the n times m, or just a to the n m. Okay, so if I was showing an in-between step here, it's barely an in-between step this time, but I might show it as like 5 times 4 if you want to be really clear. And so that would be 2 to the power of 20. So 2 to the power of 20 is a simplified version of 2 to the 5 times, or 2 to the 5 to the power of 4. So next one here, power of a product. If we were to do this one, the logic of it, we'd have 4 of those. So we'd have a 3 times a 2, 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 all the way along. And so the trick here is to recognize that order of multiplication doesn't matter. And so this could have been written as a 3 times a 3 times a 3 times a 3. And then after that grouped 2 times a 2 times a 2. Got a 2. Right? So that gives us 3 to the power of 4 times 2 to the power of 4. So if we're looking at what to say about the logic here, what happened? Well, actually I should go where are the arrows, right? So the 4 and the 4, right? What's happening? Well, the 4 is just ending up on both of those, kind of like the distributive law, but kind of for a different reason, right? So it's shown like that. I like to put the green arrow in, as an extra, but ab to the power of n is the same thing as a to the n times b to the n. So if we were to do this here, we'd have a 4 to the 3 and an x to the 3, right? So we're just writing as single powers. We're not even really evaluating. We could do the 4 to the power of 3, but that wasn't asked for. So that's single power, simplified version of things. It's equivalent, basically. So, product. All right. Leaving blank pages for you to do on your own if you would like first, of course. Quotient, power of a quotient. It's extremely similar. We would just have 3 of these, right? So we'd have a 2 over x and a 2 over x and a 2 over x, which would be a grand total of, think of the top as a 2 times a 2 times a 2, and the bottom is an x times an x times an x. So 2 to the power of 3 over x to the power of 3. Very easy to see logic here of the 3 having operated on both of the top and the bottom. So that rule looks extremely similar. And what we have here, power of product, power of quotient, that one. All right. So power of quotient's done, right? So the final one here is just to say, okay, that's all the rules, but the combination of these rules. So if you're looking at trying to do a question like this, you have to look and just do power rules as step by step as you see them, right? So I would say, okay, well, the 5, that's the power of a product happening. And then separately, but you don't have to do it separately. You can just do it all at once. We have the power of the quotient part of it as well. So basically combining 2 rows into one there. So we'd have a 3 to the power of 5 and an x to the power of 5 and a 7 to the power of 5. And that thing's multiplying on to, very similarly, a 3 to the power of 2, x to the power of 2, y to the power of 2, 7 to the power of 2. And then if you wanted to, you could show that you extend this line, this division line, point out that we're multiplying those and multiplying those. So the overall version, 3 to the 5, x to the 5, 3 to the 2, x to the 2, y to the 2, just kind of combining them. I might have done a little bit more work on this step. So just like in the bottom, the bottom's pretty obvious because they're together. That's just your power product of power, right? That's the first one we started with. It's just the product rule, right? Two powers multiplied together. You're looking for the product of them. So that would just be 7 to the 5 plus 2. And if you wanted to do an extra step, you could, where you could rearrange things. So put this one over here and put this one over there and so on, and show that this could be written as 3 to the power of 5 times a 3 to the power of a 2 and an x to the power of 5 and an x to the power of 2 and so on. So if you rewrite the top like that, and maybe this step was happening then or something, you could easily show that this would be a 3 to the power of a 5 plus 2. And we'd have a x to the power of a 5 plus 2 and a y to a 2. So a final result of a 3 to a 7, x to a 7, and a y to the 2, all over a 7 to the power of 7. Okay? Now, it might be tempting to try and look at simplifying this, but it can't simplify. And that's because, I don't know if I said it enough at the beginning, because they're not like bases. So it was on the page, I just didn't emphasize it. But in the end, we get to emphasize this. So they're not like bases, so they can't combine. So up at the beginning here, I said exponent rules, and this is all just with like bases. And so, for example, if you had a to the 3 times a b to the 2 or something, you can't simplify this. Right? So in the case of a 7 and a 2 or whatever they were as the bases, they can't simplify. All right? So that is done. And there's your practice questions to do with it. They're all pretty straightforward. Just go ahead and do it. So like the 8 and the 9, you have like bases. So just use the right rule, put the values in place. you have any questions, as always, post them in the discussion area or email me. All right. Talk to you later.